Hello, everyone. I'm Joseph Owusu with the University of Energy and Natural Resources in Ghana and a PhD student of Autonomous University of Madrid, Spain. I will be presenting on our research work, which is titled A Miniaturized Monopole Antenna with Embedded Rectangular Notch for Ultra-Wideband Usage. This work was put together by myself, Lillian Gloria Mewu, Kwabena Markon Vincent Young, Stephen Owusu, and Melody Chiniwa. So the presentation I'll take you through the introduction, literature review, the configuration, we'll discuss the results, and then conclude. So the antenna we are presenting is in the ultra-wideband terrain, and then ultra-wideband systems are gaining strong usage, coupled with the fact that the involvement of Internet of Things in our livelihood is expanding. Our usage of Wi-Fi signal and other IoT devices employ us to have a wideband for communication. And this is where the ultra-wideband becomes useful. And it's very important to design antennas to adapt for this specific use. Most of these devices being mobile employ that the antenna should be adapted for such. We therefore went ahead to review papers in line of these features of ultra-wideband systems. One being the fact that the antenna should be compact because it involves mobile devices movement, so it needs to be strong. Also important is the fact that it needs to be the size, which have to be small and adaptable to the small mobile devices that are involved in the ultra-wideband communication. And then also need to be adaptable for high-speed transmission. So we try to review these papers in line of these features and then improve upon some of the features in our own design so as to incorporate a very small antenna, compact with good enough gain and operating in the omnidirectional antenna to relate high wideband communication in all directions. All right, so we went ahead to also employ other features such as using partial ground plane to widen our bandwidth and employing a rectangular notch in our ground plane to improve the matching. So all this trying to attain good gain with wideband to cover the ultra-wideband terrain. So the goal of our work is to build a low-loss antenna capable of ultra-wideband communication with minimum complexity. So our design is based on the lossy copper and then also trying to make it cost-effective and omnidirectional so as to be able to communicate in all directions. All right, so here we present the configuration of our antenna. It's a patch antenna employing partial ground plane with a rectangular notch in the cut in our ground plane, also used to complement the matching. So our patch is small enough and then these to create a resonance in the high frequency terrain. But this high frequency terrain, especially involving the planar, will not give us the wideband that we needed. And therefore we employ the notches as a technique from our review work, trying to improve upon the matching. So our final proposed antenna parameters are presented in table 1 over here. And then here we present the results of our return loss. So the return loss at the 10 dB gave us the operating frequency of 3.8 gigahertz to 15.1 gigahertz, which cover the ultra-wideband frequency range. And this is wide and very useful. All right, so here we present a bit of the analysis that brought us to the conclusion of our optimized configuration parameters. So one, the fact that we employ the small notch of our antenna create the resonance at the high frequency. And then the next important thing was to explore other features which will give us the wider bandwidth of interest. And then we employ the rectangular notch in our how you call it, our patch. So this widen our operating frequency. And then as we increase the length W2 of our slots, our frequency widen, but the matching gets poorer. And therefore, it's important to employ other features to improve upon the matching. And one of that was the fact that we increased the further length of the patch. So by that, it resonates in the lower frequency band, creating a better matching than previously was, which brought us to a bit increase in the size. And then we further complement this because we don't want to have a very large size. As we mentioned in the beginning, it's important to have a miniaturized antenna adaptable for handheld devices. And therefore, we explore other ones which involve the partial ground plane, which also gave us a widened bandwidth with a little bit of complemented matching. And then went ahead to employ the rectangular. So here we presented the W1, which have to do with increasing the patch length to compensate for the low frequency resonance and improve matching, which we're able to obtain that at giving us a W. If you look at it, increase it by 1 millimeter from the 11 to 12, that gave us what a poorer matching as the thickness reduces, but as we increase the thickness, the matching gets better if we look at the operation. And this was we employ, and then complemented that with the ground plane, with further the rectangular notches in the base of the ground plane, improving the matching, because that gave us a compensated wide frequency resonance. And it's also important to know that this needs to be optimized such that we don't have the partial ground plane, because the leakage from the our surface current, if we don't compensate that well, it means we are going to have a mismatch. So we have to optimize this carefully over time to try to obtain the parameters of interest, giving us the wide bandwidth with the matching that will give us the operation in the terrain with the optimized parameters. So our antenna, because we are employing the planar, means we have the advantage of omnidirectional resonance with an effect on our gain. So we're able to obtain a maximum gain of 4 dB. And then we saw that as we increase on the higher side of the frequency, the gain is higher than compared to the lower side of the frequency. And this is because the natural resonance of our patch is on the higher frequency side, which we explore the wider bandwidth using the slots, and at the same time have to compensate that with loss of gain, but with omnidirectional nature, which is good for these handheld devices that communicate in all directions. And especially in indoors where not so much of obstacle, this may find its usefulness in our IoT devices, in our Wi-Fi devices within a constrained space without so much interference to affect the gain, but needed the omnidirectional nature. So here we present the VSI, which was less than 2 for the entire operation region, which is very good. And then we also have the realized gain presented in our Fig 6B over here, realizing that the gain gets better on the higher frequency side because the natural resonance of the antenna patch is on the high frequency side. So here we presented our radiation pattern in the E and then the H plane, and we can see that we have the omnidirectional nature that we earlier discussed, and this is good for our indoor applications, which we are hoping our antenna is adaptable for. So in conclusion, our work has to do with presenting a low gain antenna which employ a notch to widen our operating bandwidth to cover the entire ultra-wideband frequency terrain. And then we employ partial ground plane and notches in our ground plane, trying to improve upon the matching and compensate the wide bandwidth resonance we're trying to create, shifting away from the natural resonance. And in effect, the gain reduces, but we have wider bandwidth. So a total dimension of the antenna obtained was 27 by 32 by a thickness of 0.742, just about 0.8. And then the substrate we used was the Roja, which is good for these high frequency applications. And then as mentioned, our design compromise of the rectangular notch and then have the VSI less than 2 in the entire operation region. And then the gain of 4 dBi, maximum gain of 4 dBi. And from the ultra-wideband frequency range that our antenna covers is very useful for wide local area networks within the LAN, within the WiMAX, Wi-Fi applications, and then in an enclosed spaces like within aircraft services in our IoT communications within our homes. This can be applicable, and its small nature, and the fact that it's lightweight and employ the microstrip, which improve the power transmission and then ease of fabrication. All this add up to the advantage of our antenna. Thank you, and I welcome your questions in the comment section and in my mail. Thank you.